Travis came to talk to me about giving a presentation, and he wanted specifically a presentation about time that preservation failed. And he had this bridge in mind, so the question was, what happens when preservation fails? To summarize, this is what happens when preservation fails.
Demolition progressed toward the three tied arches.
Ignoring the fact that they failed to blow up one of the arches. I can't just leave it like that, even though that really does summarize what happens when it fails. I'm going to start by talking about the history of the bridge. It's the Alsea Bridge. This is a picture of it just before it got blown up, with the construction of the new bridge going on in the background. And that was in 1991, roughly. So, give you a sense of the timeline. I'm going to run through some of the problems that they had from construction, talk about how the bridge continued to deteriorate throughout its just over 50-year life, and then talk about what we learned from that and how our bridge preservation unit actually came out of that. So I can't talk about the bridge without talking about Condi McCullough. He was the state bridge engineer from 1919 to 1936. This bridge was built just at the very end of his tenure. So the Coast Highway was the last section of the Oregon highway system, really, of the major highways to be built. This map is from 1929. The Coast Highway out here, at this point in 1929, is not continuous. Out on the coast, there are large chunks that did not have a road at that point. But they recognized the potential for tourism from California coming up the coast and really wanted to develop it. So by 1936, so quite rapidly, they had built the rest of the highway. But what they hadn't managed to do was finish the bridges. They still had 6 major ferries. They were big choke points. They took lots of cars every day. And they didn't run in bad weather, which there's lots of on the Oregon coast. As a result, as soon as the WPA came up with funding, Oregon stepped up and said, yes, we can build 6 bridges in 2 years. 6 major bridges. And they did. The first of those bridges was down at the Rogue River. Of those 6 bridges, 5 of them still exist, and we have impressed current cathodic protection systems on all of them, I think. Alsea Bay is the one that didn't survive. Here's a map of where it is. It's kind of in the middle of the coast. It's very close to the ocean, but all of them are. There's this sand spit out in front. At the time that the bridge was built, there was no development there. There's now lots of houses. So it's a little bit more sheltered of a site than it used to be. You can see in this map the big sandbar. The map is actually from a 1983 study that we'll talk a bit more about, but that sandbar's always been there. The bridge itself, this is the card from the maintenance file from the 1930s. So as soon as the bridge was completed, they put this card together, put it in the file. We had it all microfilmed, which is why it's really poor quality. From the north end, the bridge, it's 2 reinforced concrete deck girders, 3 deck arches, 3 tied arches, 3 more deck arches, and then 30 deck girder spans. Those deck girder spans are the part that go across the sandbar. Total length was 3,000 feet, roughly. It's 2 12-foot lanes, 2 4.5-foot sidewalks, constructed for $750,000 finished in 1936. It's kind of a cut-apart view of the bridge. You can kind of see the channel. It's not a very deep channel. There's not really a harbor. It's just for fishing. And there aren't very many boats. Today there's almost no boats at all in the area. The rest of it's just sand, which is also part of the problem with having a ferry here, is where it could land changed every time the tide moved. Looking a little bit more detail at the arches, because they're kind of the highlight of the bridge. Condi McCullough was known for using Considaire hinges to make so that when the arches were cast, they were considered hinged arches for dead load. The hinges were then fixed in concrete so that under live load they act as fixed arches. Even the tide arches had those hinges. The tide arches also for the tie member have a large steel section. In this particular case, I believe it's eye bars with pins. So I'm going to talk a little bit more about the construction. They had problems from the very beginning. Partially because it was a WPA program, they had a lot of restrictions on how they could acquire materials, a lot of guidance offered. So one of the changes they had made to their specifications, and at this point they've built thousands of bridges successfully. They changed their specifications so that the piles, for the pile supported footings, which is all of them, because it's all in sand, required a certain density of timber, and it was in rings per inch. But they also had to get their timber within a certain area, locally. And the contractor couldn't find any old growth Doug fir in that area that would meet the requirements. And so he came up with, well, I've got hemlock that'll meet the requirements. And nobody thought to say, well, but that's not gonna last very long. So we'll come to what that led to. Also, the aggregate. This is the washing station for the gravel. You can see they're pulling the water directly from the bay to wash the gravel, which they were pulling also from 10 Mile Creek just upstream. 10 Mile Creek, they were pulling it from a gravel bar right at the mouth of the creek, and then washing it with seawater. Now we know that chlorides are a problem. Back then, at least they were getting the sand off. Of course, they were also getting their sand from a beach. There's not much of a beach left here because all of the sand went to Alsea Bay. The reason we know this is where they got their sand from was because the community here was complaining because their fishing was falling apart because all of a sudden there was no sand for the spawning of the fish. The sand never came back. So we still technically have a state park beach there. You can see how little beach there is. But that's not the end of the problem, because typically people say Alsea Bay, yeah, it fell apart because we used beach sand in the construction. But we use beach sand in almost all these bridges. Both of these, this is Yaquina Bay, used exactly the same sand. The lower one is the bridge at 10 Mile Creek. It was definitely built using that same gravel, probably that same sand as well. In fact, you can see the gravel bar in front of it, and it's in an even more exposed location. That bridge doesn't even have an impressed current system on it. It's doing way better. So clearly something else was wrong. I think this is what the problem was, but there's still research needing to be done. They used a concrete additive. They were pushed to do some more experimental things on this bridge. I don't quite know why this bridge was chosen, but they used a material today we call diatomite. At the time they called diatomaceous silica. The material they used was very different from the material we have today. It is a natural pozzolan. If you grind it fine enough, it works great. If you read the ASTM spec for the natural pozzolans, you need to have at a maximum 1% retained on a 325 sieve. Super fine material like silica fume. This material, their spec for its use was that less than 10% had to be retained on a 30 sieve. It's basically a sand. Silica, you might recognize from ASR, from alkali silica reaction. When used in large particles, you get ASR. This is basically opal. It actually looks like this, gets ground up. There's a couple of sources of it in Oregon. They're no longer mined, but it's perhaps one of the few cases where we've had ASR in an Oregon bridge. They also had other problems. The picture of the railing is from 1935. It's a year before they opened the bridge to traffic, and you can already see efflorescence coming out of the rail cap, flowing down the rail. I don't know the exact cause of that, and none of that rail still exists, so I can't really do any tests. They also had problems with scour during construction. That came back as well. That was the work bridge. You can see they were having problems with the tidal nature of the bay. Also, I'm calling this completion question mark. In their specs, they were required to coat the bridge with a waterproofing system. It didn't specify what that waterproofing system was, and it was never done. My thought is that if they had actually done that, perhaps the bridge would still be around. So, how it deteriorated after that. 1937, the first inspection. We actually have their inspection report. October 1937, they were already worried about scour. They didn't notice any. That doesn't mean there wasn't any, it just means the sand filled it back in again. There are cracks already in the sidewalk and the deck slab, in the center of the arches, and around the middle of the south approach. I don't know whether they meant the middle of the south approach meaning all of those 30 spans, or whether they just meant a couple of spans in the middle of it, because this is all the detail I've got. They also had some problems with the expansion joints. Those continue to be a problem. At this point, the inspector recommended that they seal all those cracks. That never happened. I have their maintenance records, how much they spent on the bridge. The only costs between 1937 and 1954 was they replaced some balusters in the rail. And again, I don't know if the balusters were caused by somebody hitting them with a car or whether it was that they had fallen apart. 1954, the hangers in the tide arches started spalling. This is less than 20 years after the bridge was built. The hanger rods are already spalling concrete. They did actually patch them at this point. 1968, 4 of them are already spalling again. The bridge is not doing well. They've got cracking, widespread cracking that needed to be sealed, and again, wasn't sealed. This is talking about a preservation failure. They kept having opportunities to solve the problems and kept not doing it. 1968, they probably didn't do that work because they had a bigger problem to solve. They had a scour problem. At some point, those hemlock piles had gotten exposed and rotted out to the point where one of the piers had actually settled more than a foot. So they came in and installed this retrofit on, I think, roughly 18 of the different piers. The retrofit's kind of hard to understand from this, but they drove extra piles on the outside of the bents, cast a new cap, put pre-stressed beams over the top of that, and then tied the old footing to those pre-stressed beams with steel hangers. This repair was done in 1968. This is what it looked like a few years later. It's in the tidal zone. It gets wet regularly. Those pre-stressed beams did not like that very much. And by 1973, the ends of all of the beams were dripping with rust. They knew there was a problem with the strands. There was cracking in the center of many of them. So they decided to install a cathodic protection system. It's a galvanic system. Luckily, they didn't try and run a current through it because that would have been even worse. But they did have a problem with the way they connected the wires. They used a silver material to attach the wires. So actually their great cathodic protection system protected that silver really well and actually led to more corrosion of the steel. So by 1976, the cathodic protection system had completely failed, and the chemist for the state, the important line in this is, the probability that several of the beams are near or in failure is sufficiently great. This is less than 10 years after they were installed in the bay. This is the first moment where they start recommending that the bridge is replaced. It is less than 50 years old at this point. 1983, people are sufficiently concerned with the chunks of concrete falling off the rest of the bridge that they hire Parsons Brinkerhoff to come in and do a report and make a recommendation as to what they should do about it. They didn't have very many pictures, sadly, and I don't have the original report, so the photos are all terrible quality. But this is about what it looked like in 1984. Their main recommendation was just to remove all the loose concrete for now and then replace the bridge. So they went out and removed all the loose concrete so at least it wasn't falling on people, and they continued to do that for the remainder of the life of the bridge. At this point, they said that if nothing happened the next 5 years, at the end of 5 years, they'd have to basically restrict the bridge. And that's about what happened. 5 years later, they had the new bridge under construction, and they switched to weekly inspections. This is 2 of the inspections. The weekly inspections are to remove chunks of concrete that are likely to fall on traffic. They have through arches, so there are chunks of concrete to fall on people. The first report is from 1990. There's extensive corrosion, cracking, and spalling throughout the deck and superstructure. They also started having scour problems again at this point. The second set of remarks there is actually from 1991. Same sentence, extensive corrosion, cracking, and spalling. Many stirrups near midspan of the deck arch beams have 75 to 100% section loss. This is right at the end of the bridge, and we've already seen this once before. I was going to show the video again.
Demolition progressed.
As we saw
toward
before, the
three-tied arches.
bridge gets blown up, and this is the new bridge in its place. If you remember from that video, at the time they blew it up, they actually damaged the new bridge. Large chunks of concrete fell and flew through. We've already had to repaint this bridge twice, the new one. Once at the ends of all the floor beams because of the damage from the explosion, and then again recently. This bridge actually is in good shape, luckily. We finally got it right. And we just had the post-tensioning inspection completed on this span, and it's in good shape. This was in 1991 when they finished it. That's not the only fallout, though. The old bridge was really well loved by the community. They really hated to see it go. There were actually obituaries put in all the different newspapers for it. At the time that they closed it, at the time that it opened originally, they'd had a big ceremony. They'd had a court of princesses who'd driven across the bridge as the first car. At the time that they blew the bridge up, the last car across the bridge was one of those princesses from the court. It tells you how short the life of this bridge really was. Bridges are supposed to outlive the people who built them. But everybody remembered the building of this bridge. And as a result, ODOT now funds partially a historic bridge interpretive center at the site. They actually built this building, all these tiles that you see on it, that form the image of the old bridge, were all contributed by the community members. They all gave a donation and built this building. And that tells you how much people love this, and that is really what led to us having a bridge preservation program. We recognized as ODOT that we could not allow that to happen again to any of the others of those big bridges. And the program's moved on from just the big bridges. The first one to get a cathodic protection system, widespread, was Cape Creek. That was completed in 1991, the same year they blew up the other bridge. We actually have plans right now to go back and re-zinc that bridge in the next couple of years. The zinc has lasted 30 years, roughly, or will last 30 years by the time we get out there. We have 13 bridges with impressed current cathodic protection, with 2 more in development. And when we get to those bridges, they're in the condition of the bridge that you're seeing on the left, which is not significantly different from how Alsea Bay was in 1983. If it had lasted another 10 years and been in that condition, we could have saved it. We knew how to do it by 93. So if they had had that coating system, if they had sealed those cracks, we could have saved that bridge. So talk a little bit more about our impressed current system, just because I don't know how familiar people are with it. We do significant patching. They tried patching Alsea Bay once. They couldn't get it to work. They gave up. We do extensive patching. We have detailed specs if people want those. We then wire everything together so there's continuity and arc spray it with zinc. We run a current through them constantly. Some of them have been turned off, but they still seem to be working pretty well. To conclude, the replacement cost in 1991. So remember the original construction, $750,000. Replacement in 1991 was $52 million. At that time, they estimated that rehabilitation would have cost more than that. They didn't say how much, they just said more. Today, we would estimate, based on deck area, that same bridge that they built would cost about $225 million. I think that's probably a low estimate, but that's what our bridge planner gave me. I estimated the rehab at about $60 million. That includes doing all the footing work, and it's based on a cost data from the other bridges that we've done impressed current cathodic protection. So if that bridge had survived, if they had done that work, we would have saved it. Not just that we could have, but we probably would have financially. So that's my presentation.